I kind of want to start off by showing a picture of all the different things that are going on in my lab. So I'm Professor Dylan Mosey. I'm a new faculty member here at Virginia Tech, and I'm all excited about robots. Like, that's what I study, that's what I teach, and I teach one of the core courses in the robotics program here at Virginia Tech. So in this slide, you can see basically a variety of pictures that I've taken or I'm in, kind of showing what I do, what I'm excited about. And all of them, you see mainly two things. You see some type of robot or robots, and then you see a human. And that's really what I'm excited about, how robots and humans can learn to work together. And that deals with issues of trust, collaboration, cooperation, and learning. And really what I want to focus on today is that last one, is how robots can learn from the humans around them. And the main insight here is that humans are often experts. Humans know what they want these robots to do. And so robots can gather a lot of information about the world, about the tasks they should be doing, just by learning from these humans that are nearby. However, this talk is really not about like me or my work. This is about Virginia Tech and you, and how this could be something of interest to you in your studies at Virginia Tech. So if at any point you want to talk about something different, or you have a tangent that you want to go off of, or you just want to hear more about a specific topic, please let me know, and I will try to monitor the Q&A as best as I can. It's kind of hard when you're looking at multiple screens and talking, but this is for you. I'm more than happy to focus on something that you might be interested in. Really, what I've set up today is basically a talk that goes through a variety of different things that are going on in my lab that I'm excited about, that have to do with like this larger topic of robots learning from humans. But this talk, as I mentioned, is for you. So please stop me if there's something you want to hear more about. Okay, so I thought it would be fun to start off with a video, actually. And this video, it's kind of cartoony, but the idea is actually this is a video from Toyota. They're making a city in Japan that they're calling a woven city. And the idea behind this city is it's going to integrate multiple different types of autonomy alongside humans. And so at the beginning of the video, you saw like self-driving cars by people. Here, this is like a delivery system that's going underground. These delivery robots are taking things up to people's houses so that people can then use those within their homes. Also in this house, you can see a couple different robots. One on the far right, there's a robot that's helping this gentleman make dinner. And on the left, there's more of like like a toy-like robot that looks like it's good for, talking or communication, kind of like an Alexa. This one's one of my favorite parts of the video. It's a human that's kind of jogging across the street without paying much attention. You can see one of these futuristic self-driving cars drive up and knows to stop, even though the person is kind of maybe isn't following the traffic laws as they cross the street. Here's another shot of the different robots in the person's house. And finally, their concluding shot is this drone that's flying above the city. And what I like most about this video is it highlights a lot of different ways where humans and robots can work together. And while it might look futuristic, we actually already have several of these types of interactions already going on in today's world. So just going clockwise in this video from the top left, this is a self-driving car. This is a Waymo self-driving car. I used to live in the Bay Area, so I'd see these all the time. And this car needs to know, hey, this gentleman in the bike, he might be crossing the street unexpectedly. You have to deal with that. On the right, top right, we see a lady who's working with a robot. This is more in a manufacturing sense. So for really big manufacturers, they can just buy tons of autonomous robots and they don't have to do anything with them. But for smaller and mid-sized manufacturers, they need to be able to teach their robots to be able to work with many different parts as opposed to just doing one thing for their entire lifespan. And so this woman is working with this robot to teach it a new task. Bottom right, this is going to be something I'm going to talk about more today. Assistive robots. This is a wheelchair-mounted robotic arm. These are commercially sold and available today. Bottom left, another very common robot application today is robotic surgery. This is a Da Vinci surgical robot, which is, you could imagine this working to perform a very minimally invasive surgery on the person's body to help maybe remove cancer or a tumor on that body. So these are all, I had the futuristic vision, and now these are all pictures of what's actually happening. And across all these different things, one of the big challenges are we can build the robots. Right? We have the technology, we have the hardware, we've got the motors, we've got the batteries, we've got the computers. We have all the different components we need to build these systems. The challenge isn't creating the robots. The challenge is figuring out how do we make these robots intelligent, right? How do we make them useful in the world around us? And my sort of approach to this bigger problem is I kind of argue that programming the robots from scratch, like in a factory or in a lab, is always going to be doomed to fail. There's always going to be scenarios which I, as a programmer, just didn't anticipate or didn't think about. So what would be better is if these robots, sure, we give them a baseline program, but they can also go out into the world and learn just from the humans around them. Like, see, oh, this is how this human's doing this task. I can do the same thing, or I can emulate that. So I want to develop robots that are intelligent enough to learn from humans in order to do more complex tasks seamlessly through this interaction. And so there are three components to this work that I'm going to talk about today in bits and pieces. The first one is just, okay, if you want to deal with humans and robots, you have to be able to put them in the same space, right? It has to be a safe interaction where I can grab the robot can bump into me, and there's no danger posed to either of us, especially me, the human. Second, I want to make sure that my robot, so I've got some hold up on the PowerPoint. I want to make sure that this robot can learn from the humans it's around, right? I've got this system now, the human and robot, they're in the same place. How can this robot extract information from me to figure out really, hey, this is what the user wants. This is what I should be doing. And the last thing, this is more of a control theory problem. It's, okay, I've learned something from the human. I've applied this machine learning, I've applied this AI. I've gotten some information. Now, what do I do with that? How do I translate this information into motion or behavior in the real world that is helpful? And that's kind of like how the robot makes good decisions based on what it's learned. So this is the cycle generally that I focus on. This interaction between putting humans and robots in the same space, hopefully learning something from that, and then making good decisions based on what we've learned. So I kind of want to go through a variety, just a set of questions that I often think about, and then different ways I've been trying to solve them in my lab at Virginia Tech. And the first question that comes to mind, the first obvious question is, hey, how do I make this process safe in the first place? How do I make sure that it's safe for the humans to work alongside these robots? And in this photo, it's kind of hard to see. This is actually a gentleman who's using a rehabilitation robot that I helped build and control. And this guy's had he had a pretty severe spinal cord injury, and so he's trying to regain loss of motor function by working with this robot. But in order for that to happen, I need to make sure this robot that this gentleman is physically interacting with is safe. It's not going to harm him. It won't present any threats to him. And that's kind of, this has been an ongoing story in robotics. Like on this left photo, this is kind of traditional robotics, like what we've been studying since the 90s. These really rigid, big robots that can do things like assembling cars. That's a pretty common application for robots. And this is what you're going to see in large factories. More recently, though, we've been thinking about, okay, how do I take these robots that are originally in these factories and move them towards homes, so they can be around people and work with people. And one of the main things that we've found that we needed for that to happen is for the robots to be compliant. I can push and pull on these systems, and they will give, as you can see here, one of my collaborators, Andrea, is pushing on this robot, and it gives, it yields as she pushes. And that's great, because if it bumps into her now, it's a bit of a safer system. So one of the things, and this is the most mechanical engineering part of my talk. The rest of it will kind of go off into different spaces, but I want to start off with the most build it, test it part of the talk. So in order to really understand the fundamentals of how do we make sure that these compliant systems can work and make things safe, we built a really simple linear actuator. We've got a motor on the left, a spring in the middle, that's going to be the source of our compliance, and then this weight on the end. And I just mentioned, hey, compliance makes things safe. When something's compliant, it's going to be a lot better to work with. Well, actually, that's true physically, right? If something's soft, it's spongy, that's great. But when we try to control it, when we try to make that system, let's say follow a sine wave or make good decisions, that compliance actually adds some control challenges where here, a very simple controller that would work really well for a rigid system causes this system now that is compliant to oscillate and become unstable. This is what we don't want. Actually, after I filmed this video, the system broke and I had to go about fixing it again. So compliance is good from a physical point of view, but how do we make sure that we can actually use that compliance effectively? And so one of the things that I was thinking about to solve this problem is just making sure that the system dissipates energy over time. Energy is something that if I'm building up energy, I'm going to oscillate more and more. If I dissipate energy, I kind of relax to a steady state. And what we did is we kind of came up with sort of an overall relationship or a control law that if we satisfy this mathematical relationship, we will know that our system is going to be stable no matter what the human does. If I flick the system, if I pull it, if I push it, no matter what I do, this system will be stable if I just follow this control law. And it's got some interesting extensions because some of the robots that are actually commercially built and sold today actually have the type of joints that I showed in the previous video, these simplified joints. And then other robots don't have these specific joints, but they have a lot of the same fundamental ideas from these joints. And so here's like kind of the comparison when you include this control, let's say control law or control guarantee. On the left is what I had before, where if I flick the system and it oscillates until it breaks, and until it breaks. On the right is I can do whatever I want. I push the system, pull the system, whatever. And because we've satisfied this control requirement, I now can make sure that my overall system will relax and go back to a steady state. And so this is kind of one of the reason I included this in the talk is to give you a flavor of one of the key components of robotics. Robotics is very broad. There's a lot of different angles for it. One angle that you could focus on, if this is what captures your interest, is building these systems, building exoskeletons, building these robots. And there are many faculty and labs at Virginia Tech that do this, building quadrupeds, etc. And then figuring out, okay, I've got my system, I built it. How do I make it do what I want it to do? How do I make it, in this case, safe? And then you're going to get into things like control theory and dynamics, etc. So this is just one flavor of robotics I just want to mention. I want to throw out there is that this is one thing that you could focus on if this is something that's interesting to you. Oh, I should mention this. So this is like the line, the solid line here is what like the theory told us would be the cutoff point. And these circles are, when we experimentally tried this, like when we built the robot and tried to do it, we actually got the points where we got the system to break were these circles. So just an example of how you do the theory, and then hopefully you match it pretty well when you put it into practice. Okay, so the first part of the talk, I try to convince you that we've got some good understanding of how we can make robots safe. Right? We can make them compliant, and how we can actually use that compliance in a meaningful way. We can make sure that this compliance system is stable. The next question, this is what I really get excited about, is, okay, I've got a safe robot, great. Now what can I do with that? How can I actually use that to do something meaningful? And the first question that I kind of had, this goes back to my time in graduate school, which was, how can robots learn from these physical interactions? I'll let the video play here on the right. Yeah. So here I am, I'm trying to pour a cup of coffee. I see the robot, it's too high in the air, so I want to grab it. And I have something in my head I want this robot to do. And then I should learn from that, hey, like, Dylan wanted me to go close to the table. Like, I can do that. And when I let go, now the robot has learned from that interaction, is now behaving in a different way. So this is just one like very simple example of how I envision robots learning from people in very close quarters, right? I can now physically grab the system and show it what I want, and it learns from that very quickly and updates its understanding, maybe of the task that it should be doing. So how do we do that? How do we think about that problem a bit more generally? That was like the desired, how do we get there? Well, I want to go through an example with my friend Ellis. So Ellis is looking at this robot arm. This is, again, one of these commercially sold robot arms. This one's made in Canada. And he sees that it's holding this cup of coffee, and what he really wants the robot to do is to carry this cup of coffee a bit closer to the table. And the idea being that, if the robot were to accidentally drop the coffee, if I'm carrying it close to the table, it won't fall so far and break. It's just a bit safer for everyone. And the robot is not trying to antagonize Ellis. Like, it wants to do whatever Ellis wants it to do. So it's trying to align its values, its purpose with Ellis. The problem is the robot doesn't initially know what Ellis wants. And so when Ellis comes along and grabs the robot, changes its behavior, the robot's not really sure what to do with that. Like, what do I really gather from that interaction? And one kind of state-of-the-art or traditional way for robots to deal with this is to be compliant, like we just showed, to act like a spring and let Ellis push and pull on the robot so that it's safe. But then as soon as Ellis lets go, to go back to doing whatever they were doing before. So in this example, you can see Ellis lets go, the robot kind of springs back to moving high up in the air. And so he has to keep interacting with the system to show it, hey, like, I want you to stay close to the table. That is what I really want you to do. And so sure, this works. You can imagine yourself standing, working with this robot and continually pushing it down to make it go close to the table, but it's not very efficient, right? Like, ideally, the system would learn from one or two examples of, oh, I get it. Like, I should stay close to the table. I understand what you want. And so this is really one small part of a much larger and challenging problem in robotics and AI in general. So I'm like plugging a book that's kind of related to this topic that might be of interest. It's called Human Compatible. And really the issue is if we keep making robots that are better and better, right? We get better at programming them, we get better at building them, they become cheaper, whatever, they become more widespread. At some point, the question becomes, how do we make these robots, we've got the technology, how do we make them really do what we want them to do? And I'm not making an argument that robots are like going to cause problems or like intentionally rebel. It's more of we need to be very precise and careful about how we tell these robots to behave. And I've got a simple example here with this vacuum robot. So imagine that you've got a vacuum robot and you tell the robot, hey, what I want you to optimize for, like what I want you to do in the world is to pick up as much dust as possible. And that sounds reasonable, right? Like, okay, yeah, tell my vacuum robot to gather as much dust, like that'll clean my room. That's perfect. What actually ends up happening is the robot thinks about it and it's like, okay, the way I can do this is by picking up dust, spitting it back out, picking up that same dust and spitting it back out, and continually repeating the cycle. In doing so, it maximizes the amount of dust it picks up, but it doesn't really do what we ultimately wanted. And so there's a fundamental challenge of how do I make it clear to the robot what it is that I, at a high level, wanted to do. And this physical interaction that we're talking about is just one example of this larger problem of humans conveying to robots their goals, their rewards, their objectives, so these robots can follow through. So I'm not going to really get into any detail on the math. I just kind of want to give you a sense of how this happens. And what it really is the robot starts off by trying to maximize what it thinks Ellis wants it to do. And then Ellis interacts. He grabs the system, he pulls it, he changes its position, and so now it's up to the system to kind of learn from Ellis. One second. I want to make sure that this sharing is working the way I intended. Let me switch really quickly. Okay, I'm going to put myself here. I don't know if you could see me previously. But yeah, it was. Hopefully you could. I imagine it'll be disconcerting just to see the slides and hear someone talking to you. With that said, is it still like you can still hear and see the slides? You can see me. Is everything working correctly? Yes, awesome. Thank you so much. All right, so let's get back to this. Sorry for the interruption. So here we've got Ellis, and he's trying to show the system, hey, like this is a better way to do this task. I want you to move closer to the table. And that's what the blue line, the teal line, is supposed to show. And what I want the robot to really learn from this is actually to extract an idea of what Ellis's objective is and update its underlying understanding of, hey, what the task the robot should be doing is. If it does that, it can then replan. It can be like, okay, I get it. Like you have a different objective than what I originally thought. I originally thought you just wanted me to go in a straight line from the start to the goal, but now I get it. You want me to follow this curved path that goes closer to the table. I can replan and I can execute that. And so the final system should look something like this, where again, the robot starts off a little too high in the air, Ellis grabs it, pushes it close to the ground, and then he releases. And the system learns from this, oh, okay, this is your new objective. I can replan and I can optimize for this. And so that leads to this better behavior that is what we originally wanted the system to do. So if you're interested in this type of work, one thing that we often do is user studies, where we invite a variety of usually students, undergraduates and graduate students, to try out these different algorithms that we're developing, and we sort of see what they think. So here's an example of a user study where we're going to try a variety of different tasks, and users are going to try to show them about how to do those tasks, and then we're going to record some qualitative and some objective and subjective results. So here's the video you just saw. On the left, this is like the default setup, kind of what we talked about earlier with the robot being compliant. And so when these users push on it, it just goes back to what it was doing before. On the right is this proposed learning algorithm that we've been working on. And what's fun is we're able to do a variety of different things. Obviously move close to the table. We've kind of talked about that a bit. Here's a different one. Here we've got Jaime, who's trying to teach this robot to carry a cup of coffee upright. And as it starts off, the robot's carrying this cup at an angle. And so he has to keep interacting with the system to show it, hey, I want you to go upright. On the right, though, you can see the robot's like, okay, I get it. Like, this is what you really wanted me to do. I can update my understanding of the task and optimize for this new thing. Let me show one other example. This would be a great time if you have questions about this part of the talk. So in this last example, we don't want the robot to carry this cup over the laptop. There's no water in the cup. I didn't want any water to fall on my laptop. It's just an empty cup, and we just don't want to move it over the laptop again in case it falls and breaks the laptop. And so users are trying to show this robot, hey, I want you to not to move in the airspace above the laptop. And all this is the same algorithm, right? The same method that we've developed. It doesn't just work for that one thing of moving close to the table. We're able to generalize this to do a variety of different tasks that a robot can learn from the user from these physical interactions. Okay, so that was fun. Like, I really enjoyed that. I love that idea of how robots can learn from people from these physical interactions. But the next question that I had, and you probably are thinking this too, is, okay, so that's great. Like, Dylan, you've got this thing that learns. What's the use of that? Like, what practically can you do with this system to improve people's everyday lives? And I think this is important in engineering. Like, obviously, we want to think about basic science. Like, we want to think about, hey, what is really the fundamentals of this problem? And that's one of the joys of college. Like, you get to actually see the roots of these questions and think about them critically and examine them without having to worry too much about, okay, what's the immediate application? Like, what am I going to do with this? How am I going to sell this in the next year or so? But I do like this, the flip side, which is, okay, I've got these fundamental insights. How do I translate that into something that's practically useful to the world? Maybe not immediately, but in the near future. And so one place where I've been trying to, let me move myself to the top right corner. One place where I've been trying to apply this is in the area of assistive robots. So on the left, you can see a gentleman who's using a wheelchair-mounted robotic arm. There are actually about 1 million American adults who, because of long-term physical disabilities, need this type of equipment to do everyday tasks like eating, which is, of course, something that you would like to be able to do by yourself without relying on someone else. And so this is an example of one of these systems in use. Here, the user is trying to do some very basic things: open a door, grab some Tupperware, and you can kind of see how hard it is for this user. I mean, this is a really simple thing, just reaching and picking up this Tupperware, and he has to continually interact with the system, continually try to show, hey, this is what I need for you to do, this is what I want for you to do. And the reason this is hard is because the robot arm itself has a lot of dimensions, right? It's got, just like your own arm, it can move in many, many different ways. But the way the person controls this robot is very low dimensional. He can just press up, down, left, right on a joystick. And you might imagine, hey, what if you're trying to tell your own arm like what to do just by pressing up, down, left, right on a joystick? Like, there's a mismatch there. Like, I've got this complex system, and I'm trying to control it with a pretty simple input. And there's nothing we can really do about that from a physical standpoint, because these users, due to their physical limitations, need very simple, low-dimensional systems to control the robots. This one's actually pretty complex. Another common system would be a sip and puff device, which kind of looks like a straw, and you breathe in and out to indicate what you want the robot to do. Okay, so we kind of broke this down. We broke this problem down into two parts, and I want to talk a little bit about both. The first part of this problem is the high level of, hey, I've got my arm, I see a goal that I want to get to. How do I get my arm from the beginning to that high level goal? And the second thing is, once I get there, what do I do? Like, how do I do this very precise, accurate manipulation to here pick up an orange peel? So we try to separate this, we try to address these in two parts. So just to start off with this idea of high level reaching. Our overall idea is that we can actually collect demonstrations. Again, this goes back to this, the earlier part about physical interaction, where an expert user, perhaps a caregiver or another person around the robot's end user, can show the robot some examples, just some demonstrations of, hey, these are some motions that you might want to do. In this example, I'm trying to show the robot, hey, how to move across the table and also how to reach for that table. And then we're going to embed those complex behaviors to the dimensions of a joystick. So like pressing left and right on the joystick now moves this entire arm across the table, and pressing up and down on that joystick causes the robot to do this pouring motion. So we're essentially embedding complex behaviors into these low-dimensional inputs so that people can more easily control the robot. And that was like our big insight to make these tasks easier for users, is that we can actually use this idea of embedding, going from high-dimensional to low-dimensional spaces, just to make the task a bit easier for the user to control. Again, kind of skimming over the math, but just trying to give you enough so you have a sense of what's going on here. At the beginning, we collect different demonstrations like you see in this GIF, someone kind of guiding the robot through the tasks. We then try to use this is an end-to-end learned system. Machine learning is jargon, but we'll call it machine learning for lack of a better term, where the system is trying to take what I've learned, embed it to some latent space. A latent space is just a kind of a hidden space or a low-dimensional space, and then decode that to reconstruct the actions that we actually wanted. So this is, again, the GIFs we just had from the previous slide, where now one dimension of the joystick causes the robot to pour, another dimension causes the robot to reach across the table. Just to try to make this a bit more concrete, because I know the previous slide was a little abstract. So imagine you've got this robot arm. It's very simple, 5-dimensional robot arm. Here's 1, 2, 3, 4, and then this is the 5th joint. And you just want it to follow a sine wave, right? You just want to go left and right on a sine wave. Well, intuitively, all you should need to do is press left and right on the joystick, right? Because this is a simple one-dimensional task. You should only need one dimension to control the robot and coordinate all of those joints to be able to move along this sine wave. And what we kind of found with our approach is that when you press left, the further left you press, which is basically a lighter yellow on this plot, the more the robot moves to the left. Similarly, the farther right you press, the more the robot moves to the right. And that's great at one point along the sine wave, but I want to make sure that same pattern repeats at other points. For example, what if I pressing right moves me to the right at the beginning of the sine wave, but then pressing right switches direction and causes my robot to move left somewhere else along the sine wave? That will be confusing. I don't want that. And so the consistency was one of the main things that we were focusing on when we were trying to figure out how to learn this latent space. Okay, so let's try to see how that works with actual users. And again, this is one of the common things that we kind of do at Virginia Tech, which is, okay, I've developed this algorithm, I've developed this physical system. What do actual people think about it? How do people actually work with and use the system? So we showed the robot a few minutes of these demonstrations, of expert demonstrations of, okay, this is how you could do the task. And the robot's going to try to learn from us. It's going to try to learn from us as people. And this is going to be a cooking task. Cooking was one of the most important things when we talked to actual users for these systems. Like eating and cooking were the two primary things that they were like, we want this. This is the most important thing for us to have in this autonomous system. And so we did this demonstration, this experiment, as you'll see, will focus mostly on cooking. And we're going to compare two methods. One method is you use your joystick to control every single aspect of the robot's motion. And this is what's actually sold today on these robots. This is the commercial system. The other method is going to be this, in orange, is like this learned embedding, so that you only ever have to use one joystick to try to show the robot how to do these tasks. So I'll let this video play for a second. All right, so on the left, here's Monet. She's trying to work with this robot, and she's trying to control basically every aspect of that motion. You can see how hard it is for her, right? She's getting this whole thing twisted up, and not even really moving towards the first thing she wanted to do, which was to grab this cup of marshmallows. On the right, she's already finished the task. She's already done everything, together. I'll replay the video so we can focus on that. Okay, so now I'll focus on what's going on the right. So the first thing she's doing is adding eggs. So this, again, this is kind of one of those things where it's like a little bit. It's a simplified cooking task, right? We're going to add eggs. We're going to add a flour. We're going to add an apple. And we're making what was branded an apple pie, which is maybe pushing the imagination a little bit, but hopefully you get the gist of the idea here. And so what's great is that we can make a variety of different things just by using this single learned embedding. And it makes it a lot easier for Monet to control this high-dimensional robot and show it, hey, this is what I want you to do. And I'm sure you can imagine how this would be helpful to people who want to cook in their own home if we make it easy for them to translate their ideas into these joystick inputs. But what we developed was not without, let's say, flaws or issues. So here's Hong, and he really wants to stab the particular marshmallow he pointed out at the beginning of the video. And you can see him very carefully lining everything up, only to miss the marshmallow that he wanted. So we have a little bit of an issue with our high-level reaching. And it kind of goes back to what we originally wanted, right? Like now I've gotten to the place I originally targeted. I've gotten to this high-level goal. Now how do I make sure that I'm very precise at that goal? How do I move in a very precise manner to stab exactly what I intended? And this requires a combination of two things. What we just discussed, these embeddings, are the first thing that we need. The second thing is we actually need some assistance from the robot itself. We need some autonomy from the robot. And this is commonly called shared autonomy because really the human and the robot are working together to do the task. We both are sharing control over the system. Again, to try to explain this, think about you're trying to, let's say, stab something on this plate. So you're working with a robot, you're controlling that robot using a joystick, and let's say the gripper of the robot starts off above the plate. And at the beginning of the task, the robot has no clue whether you want this tofu, the miso soup, or whether you want the rice. So it's split. It's like 50-50 on both of these two things. Well, let's say you start moving towards the rice, and you start moving this joystick towards the rice. Now the robot can figure it out. Okay, like I get it. Based on your actions so far, it's pretty likely that you want the rice. And similarly, if you were to change that up and instead move towards the tofu, the robot can also, okay, again, I kind of see you moving in a line towards this tofu. I can predict that that's what you want. And so our idea is that we're going to take this and use it to change the meaning of the user's joystick inputs. So here's like a couple of videos showing our vision. So at the beginning, you're doing this high-level reaching motion and moving towards your goal. Let's say you want to reach the red cup here. Once you get there, we can change the meaning of your joystick inputs so that now, instead of controlling where you're going, this like very high-level, imprecise motion, you can now control really fine-grained motions. Like here, we're reaching whether we want to grab this cup from the top or the side. So I'll jump right into a user study kind of showing how this works. On the left, this method is going to be the sort of the baseline of what's commercially available. Here, this is this is an eating task, let's say, where we want to make dessert. We want to stab this marshmallow, dip it in the icing, scoop the icing, dip it in this rice, and then put it on the plate. I don't know who would eat that for dessert, but that's like what we were able to assemble in the lab. I also don't really want to work with food again in the lab because food got really messy. We had to clean the lab all the time. This was pre-COVID, as you can see. But yeah, food was a real pain. Anyway, let's see how it works. So this is like the baseline, what's commercially sold on these devices. And so she's able to stab the marshmallow okay-ish. But this second thing, this is Annie, and when she's trying to scoop this icing, she really struggles doing that. She gets a little bit, but not very much. And the problem is she really was never able to align her motion in a different way. Let me stop this video and play it again. So this is going to be our proposed approach where the robot recognizes, hey, you're moving towards the marshmallow. I can help you with that. Not sure why this appeared. Let me just go back. Okay, I can help you with the marshmallow. Then once we get to the icing, you want to scoop that. You can control that precise motion using your joystick. I get that. And then you can dip that in rice. And the main difference between the two is with the basic method, she was never really able to change the meaning of her joystick inputs. And so she was always sort of stuck in this stabbing motion. Whereas on the right, she's like, the robot not only helps her get to these main targets, once she gets there, it also helps her align the joystick in different ways. Okay, this is another aspect of our work. So everything I've talked about so far has been pretty, let's say, objective. Like, this is working faster than the other one. Like, this is better because it's faster. Like, this is better because there's less measurable force. Like, these are things that we can measure. Another thing we do is we actually ask people questions, and we ask them, like, essentially, like, how much did you like this? Just in a variety of, like, more targeted ways. So here's people's responses to a variety of different questions. This first one was like, how easy was it for you to work with the system? The second one was basically, how helpful was the system? How precise were you able to be? How intuitive was this interaction? And would you work with this robot again? And so this is just another way that we can get more feedback from people in kind of a standardized way to figure out, hey, did our algorithm really work? Do people like it? Is this something we can use moving forward? Okay, cool. So that was, just so far we've only had one human, one robot. One other thing that kind of comes to mind for me is like, okay, you've got one human, one robot. What if you have a variety of robots? How do you set up a team of robots to do something? So I'm going to have kind of a simplified example as to where this could be important. Imagine you and a friend want to carry a chair. You guys want to carry this chair up these line of stairs. The challenge here is that you both have different fields of vision. You both see different things about the world. Maybe your friend sees what's in front. Behind, like the stairs that are behind here, and you see, let's see, look, you're looking to the floor, you can see kind of what's behind him. So you both like see very different parts of the world. You kind of want to work together using your forces and torques to guide each other safely up the stairs. And that's what we want robots to be able to do the same thing. So here's a simplified example where these two robot arms are now working together and they're holding this rigid metal rod. And they want to just put this rod down. Like, it's a pretty simple task. They just want to drop this on the table. The problem is there are a few obstacles in their way. So this robot on the left can see this pile of boxes, and the robot on the right can see this pile of books. But neither of them sees like the other one's obstacle. And so if they were to try to do this task completely by themselves, they both will work to avoid what they can see, but they will, let's say, counteract one another and end up just moving basically right down the middle and smacking into both. So here's like their opposite goals, right? The one on the left wants to go in front of the boxes, the one on the right wants to go behind the books. When they actually execute this, and you've got two different views, a side view and kind of a top view, they twist this rod and push on each other, but they aren't able to like avoid either, and they end up just colliding with the boxes, which is like pretty silly, right? So we want to make sure that these robots can actually use their actions and their partners' actions in order to collaborate and work together. So we can have systems of many, many robots that can coordinate with one another. And again, this is an example of how we can learn from each other in order to do complex tasks. And again, kind of brushing through it, but the main insight for this is we can split this into roles. We can have something like this is often called like a leader and follower, and what we implemented is not that different. We just called it a speaker and a listener. So the speaker is kind of the one who's conveying information, and the listener is the one that's taking in that information and trying to learn from it. The thing though is like if you always have one robot that is the speaker and the other one is the listener, you actually get pretty stuck because the robot that's always the listener never has a chance to convey its own information back to the first robot. So our theoretical analysis shows that, hey, when you've got these teams of two robots, they need to be able to alternate roles. One person speaking, then the other person speaking, you're going back and forth, just like you would have in a conversation with a friend. If only one person ever talked, you wouldn't be able to exchange your own views. And we have some other cool findings about how this, if you do talk and go back and forth, you can actually do just as well as a team of two robots that are controlled by the same computer and can talk the entire time. So let's kind of see how that works in practice. So I've got these two systems. Again, the same setup. They both see different parts of the world. But now they make a coordinated plan together where they end up moving behind both the books and the boxes. They're not resisting one another. They both are moving in the same direction. And they're able to put this object down, even though neither robot really sees all the obstacles in the space around. So just to kind of compare the two, this first plot is what happens when the two robots are acting completely independently and aren't paying attention to one another. This is like an internal resistance force, and the two robots are basically opposing one another. But once they start thinking about these roles, like speaker and listener and trading off, that's when they coordinate. They work together, and they end up doing this task with very little resistance between the two. This is what we'd like to see. Okay, I think I've got one last question that I want to discuss before we turn it over, just to sort of generally talk about robotics and Virginia Tech. And that is, so far we've always been thinking about how robots are learning and robots are, let's say, adapting to humans. But there's a flip side to that. If I work with a robot for a while, I learn about what that robot does, and I actually adapt to the robot itself. And robots need to account for that. Like there's this mutual co-adaptation between the human and the robot, and that's going to make the human's behavior different. And so the robot needs to be able to anticipate, hey, this is how the human might change their behavior over time, so I can continue to work well with this human. Again, this experiment is a little complicated to explain, so bear with me, but it's also a fun one. It's two robots that are working to play hockey. And so we're going to have one robot that already knows how to play hockey, and that's what's shown up here. Right now it's on the top of the screen. In a few slides from now, it's going to be on the right of your screen. This other robot, here highlighted in orange, does not know how to play hockey at all. It has to learn from scratch. And what makes it especially challenging is it does not see the puck. The whole time it's blind to where the puck is. And so it's learning from very low-level feedback. We tell it, like, you blocked it or you didn't block it. That's all we tell the robot. It has to figure out how to play hockey just from this very simplified feedback. To solve this problem, we use the combination of latent spaces and reinforcement learning, another, throwing out some more jargon, another type of machine learning, another type of robot learning that we can use. Where over time, the robot builds up experiences. It sees many examples of, oh, I missed it this time, I blocked it this time, and so on and so forth. It gets up all these experiences together and it tries to figure out, okay, what actions should I take based on what I've seen before in order to consistently block the puck? What makes this especially challenging is that the robot who knows how to play hockey is always trying to beat it, right? And it's like, okay, you block the puck on the right. This time I'm going to fire a different direction. I'm going to fire it to the left. And so you're going to have to be able to adapt and figure out, okay, just because I block to the right one time doesn't mean I can block the other next time. So let's kind of see how this works in a video. So this, let me just make sure it's playing. Yes. So the robot that knows how to play hockey is on the right here, and it's going to fire the puck basically in 3 directions: down the middle, to the left, and to the right. Here's our robot that's learning on the left, and this is after it's learned quite a bit. And so we give it basically a bonus or a reward whenever it successfully blocks the puck. If it blocks it right down the middle, it gets 1 point. And if it blocks it to the left, which is more like to the top of this particular video, it gets 2 points. So what it ultimately wants to do is it wants to trick this other agent into firing the puck to the left as much as it can, because that's where it gets the most reward. Okay, so this was, just to give some background on how this worked, we set up these 2 robots to play hockey. We sort of automated the entire system, and then we left it overnight and would come back in the morning and see, okay, like, did these robots learn, or like, did something break overnight? We ended up going through two of these hockey tables. The first one we like bent the middle because the robots were pushing on it too much. I don't think we broke anything else, but it's certainly possible that we did, which is part of the fun, right? So anyway, this is a very simple method where the robot is not really thinking about how the other agent adapts with it. It doesn't co-adapt. It just tries to learn a single way to block. And what ultimately happens is that for the first few hours, the robot always blocks to the right. Like, it just always moves to the right, which isn't a very good strategy. And then it's like, oh, okay, the right's not working. Let me try something else. So it slowly shifts over, and then it always blocks to the left, which is also a bad strategy. You need to be able to go back and forth and block those things. So this sort of naive method was a baseline. Okay, here's something a lot closer to what we want. And at the beginning, the robot, again, is really bad. It has no clue how to play air hockey, and so it just kind of jitters in the middle. After a bit of time, it's going to kind of pick up. This is after 2 hours of training. It's gotten some good ideas on how to block. And you'll notice that it's now blocking in different directions. You know, it starts at the top, it goes to the middle. After 4 hours, it really gets it. Okay, I need to go back and forth to block multiple shots because this other agent's going to continually try to fire maybe where I didn't block last time. And so now we're a lot happier, right? We're blocking something close to 90, like 85, 90% of the time with the system. That's good. That's pretty good for our system, especially when we can't see the puck. But there's that one last thing that we want, which is we want to encourage the robot to fire to the left, because we get like a bonus if it fires to the left. Like, we're happier if that happens. And so this is our final method with everything included, where it looks about the same. The main difference is that it purposely misses, or basically misses the puck to try to trick the other agent into always firing to the left. And it doesn't work all the time, but it does lead to a bit better results. So here, you'll notice this is about the exact same as before. It blocks the puck about 85, 90% of the time, so no change there. The change occurs in this slide, where on the left, you can see if the robot doesn't think at all about like blocking to the right, middle, or left, it just tries to block every time. It's pretty consistent. You know, it blocks 33% about each one. When the robot starts thinking about, hey, I can actually use this to influence the other agent, I can use this behavior to try to guide the other agent, that's when it starts like blocking more and more to the left. It's not perfect, but it does like trick the other agent more and more. And I like this idea of like how robots and humans, when they work together, can influence one another. The robot, of course, learns from the human. It learns, okay, this is how I should do the task. But then the robot can take what it's learned, or maybe like some things that it understands, and try to guide the human towards a better strategy as well, so that both agents are able to succeed. For example, maybe I'm working with the robot to set the table. And let's say the robot has learned really, really well how to carry a plate. So like, it's an expert in carrying plates. That might be a great time for the robot to influence me and sort of show me, hey, Dylan, I can carry the plates. I'm going to do that. You take care of the rest. Like, you should focus on these other things. And that'll change my strategy. So now, instead of my, like, I don't know, setting 2 of the places and carrying 2 plates down, I'm like, okay, I'm not going to carry any plates. I'm just going to go straight for the silverware. So that's kind of I don't think of this as like a negative. I think of this as a positive. Hey, we can use this to try to guide both agents, both the human and the robot, towards a better overall system. Okay, so to end my talk, I want to go back to that video I showed at the beginning, again, to emphasize all the different ways that humans and all the different spaces, let's say, where humans and robots can interact. It could be autonomous cars on roads. It can be delivery systems working by themselves. This would be an example of multiple robots needing to coordinate with one another to do a complex tasks. Or it could be more of a personal setting where we have robots in the home and we want to be able to work with those robots very closely to do physical tasks like making dinner, as we saw in the slides today. So I'm interested in all different sides of this problem, and you can find all these different aspects of research at Virginia Tech. So I'll end with this slide again. So this on the bottom right, this is my lab's website, collab.me.bt.edu. And you can Google search it probably a bit faster. But if you want to like read more or see more pictures or more blog, we've got some blog posts. Anyway, if you want to see some more stuff about what's going on in the lab, videos, etc., feel free to check this out. This is, of course, in addition to all the other amazing websites at Virginia Tech, which could be very helpful. Just throwing out one more potentially helpful one for you to look at and consider. Okay, so with that, it's I didn't talk too much. I always talk too much. I'm a very talkative person. So it's 7:50, and I wanted to save this last 10 minutes or so really to answer your questions or just to chat about any part of this that you want to learn more about. So this could be either you have a specific question about something I showed that you didn't really understand. You want me to talk more about it. Could be more general, like what is robotics at Virginia Tech? Like what's the program like? We have a major. I can tell you more about how that major works. Or it could be more about the area. I just moved to Blacksburg, let's say eight months ago now. So I'm quite new to the area. I can tell you sort of my experience so far. If you're not from around Blacksburg, maybe you know more than I do. I don't know. But anyway, yeah, this time is yours. Feel free to ask any questions you might have. Okay, great. How does the robotics major work? Good question. So basically the way that this major works is, oh, sorry, can you hear me? I think I muted myself by mistake. This major is basically I don't know the right word. I want to say sub-major, but that's not quite right. It's concentration. I think that's the right word. It's a concentration within mechanical engineering. So you would be within the mechanical engineering department, and we have a robotics major within that. We just started it, which is pretty common. Like a variety of schools are just starting these robotics majors. And there's a few required classes that you need to take, and then you have a few sort of areas that you could pick your own class from this area. So the required class is actually what I teach, Robotics and Automation, which is basically an introduction to robotics, and it focuses on robot arms and how they work, how we control them, geometrically how we think about them in space, and then it deals with things like let's say control, dynamics, etc. So that's like one of the required classes. And then some of the areas where you could focus on more include like control. If you're someone who's interested in, hey, how do I make these systems do what I want? There are also classes that focus on modeling. So things like dynamics, like how do I understand this overall system? How do I think about these system of equations, equations of motion? And then branching outside of mechanical engineering, there's also several like very related classes that I recommend my students to take. Some of which are in, let's say, computer science or ECE, electrical and computer engineering, that focus on machine learning, again, defined broadly. There are a few classes that take care of that. And then there's a few other classes. There's certainly a lot of classes on control. Like if control is something you're interested in, Virginia Tech has quite a variety of different classes that you can take. So robotics is very broad. I mean, you saw that in my talk today. I started off with like building a system and ended up by having like 2 robots I bought like play hockey. Like it can be very broad. And there's even things like nanorobots or biological inspired robots that people at Virginia Tech explore. There's a lot of, I couldn't capture all that in my talk today. There's more diversity than what I showed. So that the major is a little bit open-ended in the sense that you can kind of pick and choose based on what specific areas of robotics are most interesting to you. But there are a few required like core classes that you would need for any of those. Are any of these classes available to other engineering majors as electives? Yes, although they do fill up really fast. So like I mentioned, I'm teaching robotics this semester, and I was originally only supposed to have 30 students. I let in like 44, and they all ended up being like graduating seniors in mechanical engineering because the demand was really high. Hopefully we can fix that moving forward, but they are available to other majors as electives. And like if you're in like computer engineering, computer science, or electrical engineering, or electrical and computer engineering, there are often like very similar classes that are available to you directly within your department. So we have like some classes are mechanical. There's a very similar or the same class that's offered in, let's say, electrical engineering. So yeah, obviously I'm biased towards mechanical. That's what I'm a professor of, and that's what I studied. But you could definitely do very similar things in the other majors as well. Okay, another great question. When can you decide sort of that you would like to concentrate on robotics within mechanical engineering? So that's like not, you don't need to worry about that your freshman year. That could be a decision you make sophomore, junior year, basically. That was not like a very quick, just because like at the beginning, like your first year, if you're in any type of engineering, you basically take the same classes. Mostly like your prereqs, like you'll take basics like physics, chemistry, your math classes. And so your freshman year is not extremely specialized, unless of course you have a lot of AP credits built up and you can sort of skim through some of the background classes, which I found really interesting and worthwhile. So I'm not trying to sell them short in any way. But your first year is very flexible, and it's only in your second year that you really start concentrating. And you could definitely wait until the end of your second year, even if you know, hey, I want to be in mechanical, you could wait until the end of your second year to really focus on robotics. So it's not like a decision you need to make now, for sure. Okay, here's another great question. Are you only allowed one major? No, you can definitely double major. It's harder, of course, but you can certainly double major. And it could be across very different departments. Like if you let's say, this is kind of drawing from my own experience. I was really interested in mechanical engineering, and I was also pretty interested in English literature. And so I I ended up going completely across like the STEM to the arts and sciences, and that is very much possible as well. So you can, whatever you're interested in exploring, you can do it. It just requires a little bit more work because, especially within engineering, there's like a lot of credits that you need to take. And so some double majors are a lot easier than others. For example, a double major like math and pick another engineering field is pretty doable because like you'll already be taking a lot of math classes as part of your chosen field within engineering. So some are certainly easier than others, but you certainly can double major. Is there a robotics team? Yes, there is a robotics team. And sorry, I'm trying to keep track of these. I think there's one other question as well. Please remind me of your question once I answer this first one. Robotics team, yes. So there are a few actually that are mostly student run and driven. I'm sorry, I'm trying to like think of the name of the robotics team, and I'm blanking on it right now. I've got some of the students in my class are members of that team, and just by memory, they compete in events. Like they've got a robot, they build a robot, and they go to these events that are held across different universities to sort of see how their robot compares to others. And another alternative besides just the robotics team itself is, as an undergraduate, if you're really interested in robotics, you could certainly work as a undergraduate researcher in a lab that studies robotics. For example, in my lab, I have 4 different undergraduates that currently work in that lab as researchers, kind of off and on under the COVID conditions right now. But yeah, so that's another option available to you. That would be certainly very doable. I wouldn't worry about joining trying to get an internship, or sorry, not an internship, a research position your first year, because like I mentioned, that's a time when you'll be taking very general classes. But certainly your sophomore or junior year would be a great time for you to reach out to a professor that you've had a class with, that you did well in, that you liked, and just mention that professor like, hey, I really enjoyed your class. Let's say you're interested in fluids. Let's change topic. You're interested in fluids. You took this fluid mechanics class, you really liked it, and now you're like, hey, Professor X, like I would really like to work in your lab. That's certainly, I think many faculty would be open to that. I certainly am. Okay, what are some examples of internships people have done related to robotics? That's a good question, and I don't know the answer. I know the answer like at different universities. I don't know the answer here at Virginia Tech. One that I can think of, just because I haven't been here long, I haven't really been here a summer to know like what internships people do. One example that I can give is there's a company called Torque Robotics. I don't have the website handy on me, but Torque Robotics, it's a essentially self-driving trucking company, I want to say. Yeah, I think that's right. That's in the area. That would be a great place to do an internship. Several of the people who work for that company, again, I don't want to like mislead you, but my understanding is several people who work for that company have graduated from Virginia Tech. And I know a few students that have been either in my class or I've met who've mentioned that they did an internship there. So that's the only one I can say. I'm sure there are others. I'm not trying to like disproportionately represent one. That's just the only one that I know of at this time. I'm sure if you ask other people, they can tell you more options besides just that one. So thank you everyone for coming to the open house. I encourage you to go check out other sessions that may be of interest. I also certainly consider Virginia Tech. Oh no, I'm losing my table. I've really enjoyed my short period of time at Virginia Tech. I've really enjoyed it. There are a lot of really nice people that I've been able to meet and work with, and I found it to be a really exciting environment where there's a lot of ideas, people that are very passionate about their work, and it's great to see. So all I can do is say positive things. But thank you again for joining us for this open house, and hopefully I'll see you on campus in the fall. Bye, everyone.